Welcome back everyone, Houston Math Prep talking to you about one-sided limits here in this video. Remember that just in general, the limit as x approaches some value of a function means that we're approaching the same y value from both sides. When we're talking about one-sided limits, we'll actually just be looking from one direction only. So if the y value for a function approaches some y value as the x value just approaches some value from the left side, then we'll use this notation. You'll notice our limit has a little superscript. It looks like an exponent, but it's not really an exponent of a negative sign, so thinking from the negative direction, from the left. So say the limit as x approaches a from the left, or from the negative side, of our function is some y value. So we can have a similar thing with a right-sided limit. If the y value for a function approaches some number, as the x value approaches a value from the right, then we'll use this notation here. The superscript will now be a plus sign. This is saying the limit as x approaches a from the positive direction, positive being the right side on the number line. So the limit as x approaches a from the right side of our function being the limit, then that will be the right-sided limit. Of course, if both of these limits are the same from both sides, then the general limit exists, right? We know that about limits. Let's look at some examples here. So I have the function absolute value of x over x, and I have this graph here. It has two horizontal pieces. It has a jump at the axis, and we have holes on the axis. So this question says, what is the limit as x approaches 2 from the negative direction of this function? So if I want to know limits about where x is approaching 2, then I'm looking over here on the function. So we're specifically focused on this part of the function. As I approach x equals 2 from the negative direction would be from this side. What y value am I approaching from this side? Well, I'm approaching a y value of 1, if you can tell from my labels on the axis here. So we'll get that this first one is a limit of positive 1. Think about what's happening from the positive side. So thinking around x equals 2, as I approach this point here from the right side, from the positive direction, I'm also approaching a y value of 1 because I'm on this horizontal line here. So that limit is also positive 1. So if both of these one-sided limits are the same value, then we know the overall limit as x approaches 2 on this function. We should be going to the same y value from both sides if the one-sided limits are the same. So the overall limit as x approaches 2 of this function is going to be 1 as well. So now let's go ahead and take a look at some limits involving the same function, but focusing on the less well-behaved part of the function right around x equals 0. So if we want the limit of our function here as x approaches 0 from the negative side, so from the negative side means I will be on this lower part of the graph here, and as I approach 0 on this part of the function, I'm approaching this hole, which is a y value of -1. So our limit as x approaches 0 from the negative side of absolute value x over x is -1. As we look from the other side, as x approaches 0 from the positive direction, we will be on this upper branch of the function here. And as I approach x equals 0, I'm approaching this hole, and that hole is at a y value of +1. So our limit from the right side, from the positive side of 0, is going to be +1. And because the left-sided limit equals -1 and the right-sided limit equals +1, because these are different values for the limits from both sides, then we know the overall limit as x approaches 0 of absolute value of x over x does not exist. For our next example here, we want to look at the graph of y equals square root x. So you'll notice that we actually, at x equals 0, have an endpoint of this graph. We can only approach x equals 0 from one side on this graph because it's only defined on one side of 0. So for this one, we would only ask about the limit as x approaches 0 from the positive side of square root x here. And since we approach the origin, you can tell, I think, from the right side that we approach a y value of 0, and so this limit will actually exist, and it will be 0. Looking here, I have an upper semicircle, so this function here is y equals the square root of 9 minus x squared. It has a radius of 3. You'll notice, just like the last one, it has some endpoints. It's not defined outside of -3 and +3. So if we're thinking about a limit as x approaches +3, we would only be able to approach +3 from the left, from the negative direction. So here we'll ask, what is the limit as x approaches 3 from the negative side, from the left side, on this function? Well, here we're approaching a y value that's on the axis, so that's going to be a y value of 0. If we're talking about the limit as x approaches -3, we can only approach -3 from the positive direction, from the right. So what y value do we get closer and closer to as x approaches -3 from the positive side? Again, we're approaching the axis here, which is a y value of 0. So that one-sided limit would also be 0. If we look at y equals sine of x over x, so we're smooth and curvy, except we're undefined at x equals 0 here, but the limit as x approaches 0 from the negative side, from the left side, we're approaching a y value of, if you can tell, 1 here. So that limit will be 1. Our second limit, as we approach 0 from the positive side, we're still going toward the same y value. We're not defined when we get there, but we're approaching the same y value of positive 1. So that second limit is positive 1. And the general limit as x approaches 0 of this function, since it's the same value from both sides for each one-sided limit, then that limit will exist, and it is also 1. So in this example, we have the graph of the greatest integer function. It's basically a round down function or a floor function. If we round down any number between 0 and 1, so from 0 up to 0.9999, etc., right, those would all round down, not to the closest number, but round down to 0. Things between 1 and 2 would round down to 1. Things between 2 and 3 would round down to 2. So if we look at this graph here and we say, what is the limit as x approaches 0 from the negative side on this graph? Well, here's x equals 0 right there, and if I approach from the negative side, I'm actually on this little step. It looks like a staircase, right? I'm on this step down here, so I'm actually approaching this y value from the negative side of 0, and that's a y value of -1. So this top limit here is -1. If we look at this next one and approach x equals 0 from the positive side, I would be on this step if I'm approaching 0 from the positive side. And so if I'm on this step, I'm actually at a y value of 0, right? So my second limit here would be 0. And now the general limit, the overall limit as x approaches 0 of my greatest integer function here would not exist because one side approaches -1, the other side approaches 0, and so we'll say that this overall limit at x equals 0 does not exist. Looking at some piecewise functions here, so I have most of the graph being the graph of y equals absolute value x, except at x equals 0. We've defined it to just be the value 2 at x equals 0. So you can see the graph of y equals absolute value x, but then instead of being defined at the origin here, we actually removed this point and defined the value to be up here at x equals 2. So the question is, what y value do we get close to as we get close to 0 from the left side? Well, we get close to the origin as we get close from the left side, so that limit's going to be 0. And what y value do we get close to as we approach 0 from the positive side, from the right side? Well, we also approach a y value of 0. So we get a limit of 0 there. For the last one, this is just saying, do we approach the same thing from both sides? And we do. So moving this point and redefining it up at y equals 2 does not change anything about the limit as we approach 0. We still, as we come from the left side and right side, approach a y value of 0 on this graph. Looking at another piecewise function, we have a 1 minus x on one side, that's a line, and we have square root x, which is kind of a curvy graph, on the other side. You'll notice the way that our open and closed dots work. At x equals 0, we're actually on the square root graph. You can see there's a hole here, so we're not actually on the line at x equals 0. But the limit is more concerned about how we approach the value of 0, not how we're defined at x equals 0. So what's the limit as we approach 0 from the left side? Well, I would be on the line, so approaching from the left side, from the negative direction, I'd be approaching this hole, and that hole is at a y value of +1, so our top limit is 1. If we approach 0 from the positive direction, from the right side, I'd be approaching on the square root graph, and I would be heading toward a y value of 0, the origin there, so that limit is 0. Now, because the left-sided limit and the right-sided limit are not the same value, then the overall limit as x approaches 0 of this piecewise function will not exist. Looking at our final example here, now I have a piecewise function with basically the same shapes, but the difference here now is that my line actually connects nicely to my square root graph. So when we say, what is the limit as x approaches 0 from the negative side, from the left side, here I am approaching the origin. I'm approaching a y value of 0, so our top limit there is 0. If we look at the right-sided limit, approaching x equals 0 from the positive side on the square root graph, I'm also approaching the same point, which is the origin, and that y value is 0, so our limit is 0. So now, because these approach the same value from both sides, now that these graphs are connected, we can see that the overall limit is going to exist, and the overall limit as x approaches 0 will be 0 for this piecewise function. Okay, hopefully this gives you a good idea of how to interpret one-sided limits from a graph of functions. Check out our next video where we do some more finding limits from graphs. Thanks for watching, everybody. We'll see you then.